Okay, I think we are live. Perfect. So I had like a pretty interesting idea. So I had a question about whether I should go ahead and um, do Anki like every day, and this would be beneficial for learning. So I'm much better off. And I may change this depending on like my outcomes in these first few sessions here. Um, so I was thinking like whether or not I should like review calculus every day, or it might also be interesting if I only review or only do learning things during the stream. So like I don't interact like obviously I'll have thoughts about it and I'll be thinking about it if something that I interacted with didn't make sense. But I think it'd be interesting to have all learning activities, all explicit ones, all learning activities occur within the context of streaming. Because I don't think there's been someone who has recorded the entirety of the process of learning calculus. And so I think that's pretty interesting. Yeah, so I'm going to go ahead and do that. Additionally, I'd like to probably start or I think I'm going to start streaming more. I haven't super decided yet. I'm still kind of tentative. That's definitely still up in the air. So that's pretty exciting. Yeah, I'm just all around feeling good about things. So I think today we will go as we will in the future. And we'll start with reviewing the Anki cards. And then we'll dive right in to this video. And hopefully, I guess we'll see if we'll be able to get it finished today. I'm thinking that because I've exerted so much effort in leading up to like watching this video, I think there'll obviously be some things I learn. But I think once I get into it, I'll probably, and this is actually a good thing, to make a hypothesis about like what will be learned or what will be known, because it can. This is just exerting mental effort in a good way. So my hypothesis about what I'll learn in this is I think I'll learn more syntax. Specifically, there was syntax that was used. I'm not sure in what context it was used. I think maybe perhaps the integral. Yeah, I'm not 100% sure the context, but it was in regards to limits, and how it would say like the lim and then equals. Maybe I could find an example of this. Anyway, so I think that I'll learn some syntax that I didn't know before going into this video. I think it'll flesh out my ideas on integrals and derivatives slightly. Though I think all things being considered, I'm doing fairly good on those concepts right now. Additionally, for my Anki review, I think I'll probably be interacting. I'll interact most with, or rather, my most difficult interaction will be with limits, because there are like 7 limit laws or something like that. And I didn't like really internalize them, and so I'll have that. And I think I'm actually going to, in my Anki stuff for today, or I guess recently, I've been doing coding problems within the deck, and I can't do more than like 15 in a day, or it just takes way too long. And so my preset for that was 15, but I just finished those today, so I think I'm gonna bump it up to 30. We'll see how that goes. Okay, perfect. If I have all the cards, then I'm fine with that. Okay, so we will get started. Okay. Oh. That's not supposed to be there. Oh, okay. Wrong deck. Okay. Okay, so how is calculus thought of according to a mathematician and use and how it connects to... I'm just going to edit this. I'm not going to look at the answer. Okay, so for how it connects to other branches of math, it sort of forms a fundamental sort of like the necessary foundational fundamental computational tools, I guess mathematical tools rather, for connecting things like geometry. I think the answer had something about linear algebra. Anyway, so it kind of forms this bridge, calculus does, between other areas of math, and then it is an investigation of limits an investigation of rates of change in functions through limits, derivatives, integrals, and then infinities. Okay, algebra, geometry. Yep. Okay. And this one, you could argue this is not like a super great question because I have two parts, but the sort of desire for this one is, obviously I say in use and how it connects to other branches of math, is to have like a pretty good idea of what the what a mathematician sees as calculus, or like what and obviously my idea is like, pretty bland compared to, the richness of what a mathematician would actually think about, calculus. But I think it's good in that it provides that. So the fundamental theorem of calculus is about the connection between derivatives and integrals and how they are inverse functions, where if you have a function and take an integral of it, you receive an antiderivative, and if you take the derivative of the antiderivative, you receive the same function that you started with, and then vice versa. Okay, derivative is the original function. Perfect. Okay, a limit within calculus is we're observing what occurs in a function as the input approaches a certain value. Okay, describes a function, the value that it approaches input, formalizes continuity and change, yeah. Okay, instantaneous slope. So this is another name for the slope of the tangent line, but this is when we are measuring the slope at a specific point or instantaneous point of a function. I think I'm going to say also called, a tangent line. Perfect. Okay. The concept of the slope of the tangent line. So this is the same as the instantaneous point. Yeah. Okay, it's a big S. What does the integral symbol look like in calculus? What is the concept of an antiderivative? So this is the function that you get when you take an integral of something. And the reason why we call it antiderivative is because we want to emphasize that we want to make a linguistic distinction between like an integral that, or rather, let's see, how do I make this clear? And obviously I'm expounding a little bit more. But I think this is good to jog my memory regardless. Depending on how you are interested in doing this, like you may do something like this or do much less. I know in my like daily Anki stuff, I pretty much just go straight on because most of my Anki stuff isn't, or I guess my Anki stuff exists in many areas. And so, yeah. So the concept of the antiderivative, this is the function that you get when you take an integral. However, it's not called an integral, which when we take a derivative of something, we call it a derivative, right? So the reason why that is because we want to make a distinction between infinite and definite integrals. And a definite integral would be an integral where you have like specific bounds and you're taking an area under the curve. And this is done by having one function at like a particular point, or rather, the definite integral uses two definite functions, the definite integral uses two indefinite functions, at least to my understanding so far, subtracting one from the other to understand or to return a value, whereas the indefinite integral is the family of functions that, when integrated, return the same antiderivative. And the reason being that it's a family of functions is because Oh, okay. So there's like this plus c. So we maybe f of x plus c. F of x plus c. This may be incorrect, but anyway. So the constant, when you take an integral of something, the constant sort of like falls away. And this is something I'll understand more when I actually figure out what an integral is mathematically. But because of that, I guess for some reason we'll put this constant back on, and so there is a one derivative, right? So this f of x, if we say that was the derivative, there's a family of functions where f of x and the constant is 1, the constant is 2. So you can think of like, yeah, I don't know. I think that makes sense. Okay. Indefinite integration. This is what I just talked about. This is the family of functions that you get, where you have a function that returns the same antiderivative, but this antiderivative varies on the constant. Finding an antiderivative whose function is equal to the given function, it produces a general solution expressed as f of x plus c, representing the family of functions without specified integration limits. Okay. I actually want to understand this portion here, representing a family of functions without specified integration limits. So I'm just going to put this at the very bottom of my thing. I think I will, and maybe we do this on stream, but I want to change this a little bit more. I feel like I'm just not getting a lot of value from it right now, but I could be. So, but I think so good that one is good so far. What's the difference between an indefinite and definite integrals in calculus? So definite is when you you have an integral that returns a value. So you are trying to understand the area under the curve, like this here. So if I had a function like this, and I wanted this area here, then this would be you'd need a definite integral for that. And then indefinite is the set of functions. A derivative in calculus is a measure that returns. It's a process you do on a function that returns. A derivative is when you. I'm wondering if. I don't know if I don't. Oh, maybe we'll call it differentiation. Because what I'm saying is here I'm saying we have a function, and I'm taking a derivative of it and returning a derivative. But I believe, I'm not sure if it's the case that taking a derivative is the correct terminology. It may be differentiating. I have a question for calculus. When I take a derivative of a function and it returns a derivative, is taking a derivative the correct way to say it? Is it better to say I'm differentiating the function? Or what is the correct language there? Oh, shoot. It didn't load all the way before I sent that. Okay, perfect. So that seems like normal language. Okay. In calculus, how do derivatives and integrals relate? They are inverse functions. What is the syntax for the resulting derivative of f of x? So it'd be d over d of x. I know that's part of it. I'm not sure what comes after the equal sign. Oh, just they call it f prime. Okay. So it's typically written as f prime of x. Or d of x with this syntax here. I want both of these syntaxes explained. Okay, so we'll send that one back through. Derivative operator d is denoted as d over dx, representing the operation of differentiation with respect to x. Okay. I need to edit this one. Oh, so I haven't added these the reverse ones yet. Okay. Okay, what's the relationship between a definite integral? What's the relationship between a definite integral and its antiderivative according to the fundamental theorem of calculus? So I think a definite integral has two antiderivatives that you're subtracting. A definite integral from from A to B, not AAA. It's exactly, okay, perfect. Yep, I got that right. Okay, is it proper to call an antiderivative an indefinite integral? Is it proper to call an antiderivative and an indefinite integral the same thing in calculus? It's not proper, no. Indefinite integral is about the set of all, the family of all functions for a given function that vary according to the constant. And then the antiderivative, I guess each of those are antiderivatives, so no. Okay. Okay, both of them get dropped off, though I think for integration you put it back on. Okay, so we add an arbitrary constant. Or constant. Okay, in differentiation, constant terms vanish because their derivative is 0. And integration, since the process loses the original constant value, we add an arbitrary constant to represent the entire family of antiderivatives. Okay. The integral symbol is an elongated. Okay, so this is another one that is so the integration process, you lose the constant, and so I think this is a poor way of saying this, because for a given function, but it's really a set of functions that return the same antiderivative that vary on a constant. Yeah, I don't like this. I'm actually going to delete that. I understand it, the question, but it's just not well formed. How is the indefinite integral of f of x dx expressed in terms of antiderivatives? I'm not sure. The indefinite integral of f of x dx is expressed as f of x plus c, where f of x is an antiderivative of f of x. F prime of x equals f of x, and c is an arbitrary constant. Okay. Why is the antiderivative function called an antiderivative and not an integral? I've talked about this earlier. It's to make the distinction between antiderivatives, a definite integral and a indefinite integral. D of x, or d over d of x. Okay, limit laws are used to break down a function and pull out the limits that lie, or I guess to pull out. So I'm not exactly 100% sure here because I haven't done the math yet, but the limit laws are sort of shorthand laws that help you to break down a more complex thing to derive what the limit of a particular function is. Simplify limit evaluations. Yep. Okay, perfect. Okay, so this one's incorrect. I think it's 6 names. Anyway, we have multiplication and, okay, addition to subtraction, multiplication and division, power and root, and then we have the constant law. So I think I'm going to combine. So So there really are not 5, there's 7. Okay, 7 laws. Okay, and I'm just going to double check that this is correct. I'm going to zoom this in here. Oh, there are 10. Oh, okay. So this needs to be adjusted. I'm going to see what people in the field, like what categories do they make? Do they call these like the simple limit laws, maybe? Okay, so we have... So these are the 7 that I was thinking of. Maybe we call them the 7 simple limit laws. Okay, so I'm going to open up another... Okay, so I'm not sure. The identity rule is a new one, but and it identifies constant twice. Oh, no, this is a different one. Let's see. Okay, we have the sum, difference, multiple, product. Oh. The limit of a multiple is a multiple of the limit. So I'm not super finding what I'm wanting. Okay, so these... Quotient, power, root... Constant, multiple. Okay, I think these should probably... Let's see, maybe I call them what are the basic limit laws, and that would grab me the right list. What are the basic limit laws? Calculus. Constant, limit of x, sum, difference, constant, multiple, product, quotient, power, root. Okay, we do have more than I was anticipating here. Okay, so these, I think I'm gonna maybe bring this one to review. Okay, I'll just put this on the calc review. So I'm adding this tag because I'd like to change this one, but I'd like to get through the rest of them so I can see what other ones need to be changed. Okay. This is another one of the opposite ones that I did not do correctly. Okay. Derivative. So the limit of the constant is the constant. Is itself. Okay. Perfect. I think this is similar to the constant one. The limit of the sum or difference is like the sum or difference. The sum or difference of the limits. Okay. Actually, I think I might do a quick investigation or like a quick video on going over these, because right now, if I were to memorize these, I'm using Anki right now to learn these, which is not like as effective as I would like, because typically you would like to understand things in the context which they exist. Obviously, like I understand limit laws are in this like sphere here. I think this is reasonable here though. Like obviously I have no clue what this syntax is yet. But the limit, sorry, it states that the limit of a sum or difference equals the sum or difference of the limits. So I'm pretty sure what this means is, so I'm generating this limit number, and if my limit is presently 4 and I have a -2 for my difference, or sorry, if I have a 2 for my difference, that means my limit will now be 2. So 4 minus 2 is 2, right? Okay, so I don't know how I feel about that one so far. I'd like to watch something on that, so I might send it out and then have me review it tomorrow. What's the syntax for the resulting derivative of f of x? So it could be f prime of x, or f of x, and then in square brackets d of x, I believe. Okay, no. D over d of x in square brackets f of x. So that will, okay, product power limit. So this is another one I don't know yet. Okay, and I'm going to edit that again. Yeah, so I figured out that this reverse one is actually like a Boolean field. So if I just have any content in here, it means that I would like this to be reversed, where this would be the front of the card and this would be the back of the card by default. But in a reverse scenario, this is the front of the card and this is the back of the card. So I don't know. It seems kind of odd that they used a text field to represent a Boolean field, but it just may be because of the limitations of Anki. Okay, this concept in calculus describes the value of a function. The value of function approaches, okay, this is a limit. The quotient limit law, I'm not sure, states that the limit of a quotient equals the quotient of the limits, provided the denominator's limit is non-zero. Oh, okay. This is actually less... Okay, so for... given this language, it seems that my prior understanding about we just like take what we currently have and then with the sum or difference where we just like add it or subtract it. Here it seems like we're just going to take the present limits, or I guess the total limits we've made, and put it under, or sorry, over this quotient. So yeah, and then the power one, I think this one is unique because let's see, when f of x approaches L, as x approaches a, raising f of x to a positive integer power n makes it approach L raised to n. Okay, I'm not sure where they're getting L here. Maybe this is just to specify. Not sure. Maybe this is just like any value. So, so we really care about this square here. I guess not square, but the power. So I guess it seems like for limits, we literally are just like taking out sort of the content we know from an equation, and then like pulling out these limits according to these laws, and then we just like compute it. So yeah. How is the indefinite integral of f of x dx expressed in terms of antiderivatives in calculus? It'd be f of x plus c, where c is the constant and f, and this is the family of antiderivatives. Okay, calculus is a branch of mathematics that studies continuity, change, and or I guess uses infinities. Has terms like antiderivative, derivative, integrals. Perfect. Root limit law. So I think, honestly, I think we're just going to be taking the root of the thing. I think that's where we're at right now. Okay, I'm wrong. So when f of x approaches L, with L non-negative for even roots. L non-negative for even roots. Oh, okay. Yeah, because if we have a root of the negative number, then we do like imaginary number business, which I think I could regurgitate, but I'm not really familiar with, or haven't interacted with in a while. As x approaches A, its nth root approaches the nth root of L. Yeah, I think this one is the one of them that I'll kick to tomorrow, because I'd like to have like a better understanding for calculus is the branch of mathematics that studies continuous change through limits, derivatives, integrals, and infinite series. It provides essential tools for understanding and modeling real-world phenomena in science. Oh, whoops. Calculus. Okay. So right now, I think I'll just keep with this one. I want to keep it in mind later because I will be changing it, because I'm getting mixed reactions from different large language models. So we have the power and root laws. We have the sum and difference. We have the quotient and product. And then we have the constant. Constant, sum, difference, product, quotient, power, root. Perfect. Okay. The sum or difference... The limit of a sum or difference is the sum or difference of the limits. Same thing, but for products of the limits. Resulting derivative f of x. F of x. I think it's f prime of x, or we could have d over d of x in square brackets f of x. Okay, perfect. Power limit law in calculus. This is where we just... The only one that I'm not 100% understanding is the root one, from what I understand so far. I may be incorrect in what I'm thinking, but I think we will push that one to tomorrow. I'm comfortable with pushing that one out tomorrow. Okay, perfect. Okay. I will actually be right back and go to the bathroom. Okay, perfect. I might change up how I'm doing Anki before, because I mean we're like 45 minutes in. So either I'm going to need more time for explaining Anki, or I might do it just like without explanation. I'd like to verbalize as much as what's occurring inside my mind when I'm learning these things, because that's what I feel like is my main motivation. Like, I'd like to spread memes about how learning is done. And so I guess I'll have to do some more thinking about that and refine it as I go on, because I certainly don't want to take 45 minutes every day for that. And if I did, well, I certainly wouldn't want to. I think probably 20 minutes would be like pushing it for what my desire is there. Yeah, we shall see. We shall see. Okay. Oh, I guess I still need Anki up. Nope. Add calculus. Perfect. Okay. So I think I'm gonna. Let me just follow up with someone real quick. Actually, I'm just gonna start, and then if we need to end, I'll just keep going until I have the next thing come up. Okay, let's see. Desktop audio is on.
So this is the derivative of the
We'll
original
start
function
here.
f. The integral of f prime of x is f of x. So this is the antiderivative, or the integral of f prime. So you can think of integration as finding the antiderivative. Now let's begin our...
Okay, I think I want to edit one of my cards that I had previously, because I think it was incorrect. And this is... because he had f prime of dx. I think I'll catch it on the next time.
in our discussion with limits. So let's say that f of x is x squared minus... Oh, that is a terrible looking 2. Let me do that again. So let's say it's x squared minus 4 over x minus 2. What is f of 2? Can we evaluate the function at x equals 2? Well, let's find out. So if we plug in 2, 2 squared is 4, 4 minus 4 is 0, and 0 over 0, what is that? Well, we can't figure this thing out, so that's indeterminate. Therefore, we can't evaluate the function at x equals 2. And so this is when limits become important. So if we can't find out the value of the function when x is 2, can we find out what the function will do as x approaches 2? So what happens when x is, let's say, 2.1? So if we were to plug in 2.1 into the function, you should get 4.1. Now, what if we plug in a number that's even closer to 2? Let's say 2.01. Well, if we do that, this will give us 4.01. So notice that as x gets closer and closer to 2, the value of the function gets closer and closer to 4. So thus, we can use a limit expression. So we can say that the limit as x approaches 2 of x squared minus 4 over x minus 2, we know it's equal to 4. But to show you work.
Okay, I'm going to keep going. But I just want to capture the syntax for limits. And I hadn't thought about how
That's 4 over x minus 2.
the reason why we might use something like limits here is that because if we were to like pull out an exact, like if we were just to input 2, like he said, like we'd be dividing by 0 in this case. So that's interesting. I wonder if this is, or this feels to me more like an explanatory thing and not the, it feels more explanatory than the average case for what we're doing. So we'll see.
2, we know it's equal to 4. But to show you work, what you need to do is factor x squared minus 4. And when you factor it using the difference of squares method, it's x plus 2 times x minus 2. And so we can cancel this factor. And so we're left with the limit as x approaches 2 of x plus 2. So now we can use direct substitution. So we can replace x with 2. So this becomes 2 plus 2. And this gives us the limit, which is 4. So this tells us that as x gets closer and closer to 2, the y value, or f of x, will approach a value of 4.
Okay. So I guess for a limit, limits we're specifying for limits. So for limits, we're both specifying our input limit and what the output approach is.
So even though f of 2 does not exist, the limit as x approaches 2 of the function f of x that exists, and that's equal to 4. And so make sure you understand that limits help you to see what happens to a function as x approaches a certain value.
I guess one thing that was interesting about this is that we factored out this x squared minus 4, and and then from that we are able to like remove this factor of x minus 2, right? And that enabled us to actually evaluate like given input of 2. Because presently I think that the expression of x plus 2, x minus 2, and we like factoring those out, I would think that it would be equal to this larger or like this more complex. I'm actually going to I have a question about some of the content. Oops. I have a question about some of the content here on this screenshot that I've provided, period. It seems, or I guess to describe it, this person took the limit of the function and found both the portion of the limit where we're describing what our limit is, in this case specifying that as x approaches 2, and then our output here, or rather the thing that this function approaches as x approaches 2 is 4, period. The question I have is, from my understanding of mathematics, it seems like the x squared minus 4 over x minus 2 is equivalent to x plus 2 because, as demonstrated in the picture, the x minus 2 cancels out in the function, period. It just seems odd to me that given what would I assume are equivalent expressions, given that we merely simplified the more complex version, that at that point we're able to receive a value out. Could you describe that question mark? Okay, yes, your intuition is correct, blah, blah, blah. The key issue is that the original function is not defined at 2 because substituting x for 2 into the denominator results in a division by 0. However, when we simplify the function by factoring and canceling out x minus 2, we get x plus 2, which is defined for all x. The critical distinction is that for this function it's not defined, whereas this function is always defined. So while f of x and g of x are algebraically equivalent for all x, or all where x is not equal to 2, the function f of x has a hole at x equals 2, meaning f with the input of 2 does not exist. This is where limits come in. Instead of evaluating f2 directly, which is undefined, we find the limit of f of x where as x approaches 2, which simply follows g of x equals x plus 2 for values near x equals 2, leading to the conclusion that So while this f of 2 does not exist, the limit as x approaches 2 does exist and equals 4. This is an example of a removable discontinuity in calculus. That's important to know. Removable discontinuity. But I'm going to put that in my list first. And I think we'll continue. Okay. So that sort of revealed to me, I guess, an important thing in calculus. So we had two functions that are algebraically equivalent, but for one of the functions, an input is not defined. Or another way to think about it is that, the input is not defined. So for our other function, it maps all inputs to all outputs, whereas for our initial function, we can only map everything that's not 2. So that's interesting. Removable discontinuity. It makes sense because you can't divide by 0, and so something's odd there. And it also makes sense that I can make an expression, or I can make a function break on certain inputs, right? So that's interesting. Removable discontinuity. And so it seems like the limit to me, is that we reduce this more complex function to its most simple terms, and then I guess there was two parts to that when we were generating the limit. One was that this guy who made the video, the organic chemistry tutor, he found the function, or found the value that was not able to, or that was undefined. And then after he found that, he reduced the limit, or reduced the more complex function to simpler terms, and then input what was previously undefined. That's okay. All right. Wow. It's kind of fun to notice something that seems odd, and then it has this is a part of calculus, removable discontinuity. This is a term, so it's fun to be curious about something and then find it as some understandable thing within calculus. And then the idea that we could have two algebraically equivalent functions where one of them has cannot I don't want to say process, that is not defined for some values, but that they're algebraically equivalent is pretty interesting. It makes me think that so thanks, that clarified a lot. Period. So I can have functions that are algebraically equivalent. Do these functions look different outside of just the fact that in my original function, input 2 was not defined? Question mark. Or would these functions look vastly different when graphed? Period. Oh, actually, I need a question mark there. Could you provide a JavaScript? Provide some JavaScript that can be run in the console that would map these, or rather graph these functions, question mark. So my question here is like, yeah, okay, so we have functions that are algebraically equivalent. Okay. Okay, so it looks like they are nearly identical. Okay. So they're nearly identical, but it's just that but there's a hole in this one. So let's see if that meets out in okay. Push. Okay. Perfect. And then I will just oh. Looks like I need a policy to allow this URL probably to be used. Okay, so I am fine without it being graphed. I don't want to go into a rabbit hole here. Okay, so that was important to know. So there's this idea here that I'd like to capture somehow in an Anki card. Because we have two equivalent of functions where maybe, so I'll do removable discontinuity and then capture that idea about equivalent functions where holes exist. And then I think I also want to do how to calculate the limit. I also want to see how we calculate the input for the limit. Well, let's see. I'm wondering if the limit specifies, when you describe limit, is it specifying the idea of x, let's see, idea of x approaching 2, or is it the output from x approaching 2? Oh, okay. So it's both the input and the output. Okay. Okay. So I can speak about the limit in terms of x approaching 2 and then also 4, which would occur as 2 gets arbitrarily close to 4. Or sorry, as x gets arbitrarily close to 2. So it's the process of examining approaching behavior. Ah, okay. Interesting. Okay. And this is probably distinguishing from input and output. This certainly comes from like my computer science background. Okay.
Or what happens to a function as x approaches a certain value. Now let's move on to number 2, derivatives. So how can we find the derivative of a function? The most basic rule we need to know is the power rule. The derivative of a variable raised to a constant, such as x raised to the n power, is n x raised to the n minus 1. So how do we apply that?
Okay. I want to know what the... Okay, so I want to know what the power rule is for derivatives, what the square bracket syntax is for derivatives, and then for the power rule one, I will like just briefly. I'll just list it out here. X to the n to the n minus 1. Oh, that's cool. Just putting these in, so oops. No, that should work. Okay, I'll figure that out. Let's see. So that should have backslashed. So right now, I'm in Obsidian, and this is being treated as special characters. I literally did the same thing up here using backslashes, but it's still... Okay, maybe I was using forward slashes earlier, because it works now. Okay.
Well, let's say if we want to find the derivative of x squared. So in this case, n is 2. So it's going to be 2 times x raised to the 2 minus 1, or just 1, so we get 2x. If we want to find the derivative of, let's say, x cubed, n is 3, so it's going to be 3x to the 3 minus 1, which is 3x squared. Now, if we want to find the derivative of x to the 4th power, it's going to be 4x raised to the 4 minus 1, which is 4x cubed. And so that's a simple process in which you could find the derivative of a function. But now, what does it mean? So we said that the derivative is a function that gives us the slope of the tangent line of some original function. So you might be wondering, what is a tangent line?
Okay, that's kind of crazy that the power rule is so, like, well, the transformation here looks simple. I'm interested to know more about, like, why this is. Because, I don't know, I guess I would have expected more, and I it's obviously because I don't understand this yet, but yeah, it seems odd to me that it's so simple. And obviously this is like a fairly complex relationship. Well, I guess all things considered, it seems fairly simple. And then also, another thing that seems weird to me is that we're given this. Oh, actually, no, that was fine. So I was thinking, oh, like it seems odd that this is x cubed, and when we're looking for the slope of the tangent line, like the tangent line is like linear, right? And so why do we have this, cube or square here? But the reality is that this is merely computing a number that is our slope. And so it like, if we're to graph how the slope changes, if we were to graph how the slope changes, then this would make sense. Oh, okay. Oh, all right. So, so if we have like a particular function, like this changes here, like the slope, right, at these various points. And so we would also expect the function that calculates those slopes to like follow a similar curve, right? And so, or not a well, It would follow a curve that is like amenable to that. Right. And so it sort of makes sense. I guess another interesting thing to note is that like just n minus 1 here. So we're always like back 1 for our exponent. So I guess that's interesting to know. So I'll say seems simple.
That gives us the slope of the tangent line of some original function. So you might be wondering, what is a tangent line? So let's talk about that. Let's say if we have some curve, and a tangent line is a line that touches a curve at one point. Now you need to be familiar with a secant line. A secant line is a line that touches a curve at 2 points.
Oh, okay. So I haven't done a lot. Actually, I've done 0 trigonometry since trigonometry. And so this is new. Well, I guess I've heard of this before, but never in the context of like functions, always the context of triangles and angles. So, what's the difference between the tangent line and the secant line? I think that's what they said. Oops.
Now you need to be familiar with a secant line. A secant line is a line that touches a curve at 2 points. So the slope of a tangent line is equal to the derivative of a function at some value.
Okay.
Calculate the slope of a secant line. You've done this before in algebra using this expression. It's rise over run, y2 minus y1 over x2 minus x1.
Okay. Oh, okay. Interesting. So, interesting. Okay. So, one intuition that I had before was that we're going to need 2 points at some point
y2 minus y1 over x2 minus x1.
To figure out like the slope, and then we just kind of like boil it, or not boil it down, but like we just get closer and closer. And so that's sort of what I was expecting for the function. And the secant is that. Obviously it's a different thing compared to the tangent line. And okay, but so it would seem to me that the tangent line and the I guess that's an interesting relationship there. Okay, I think I'm going to wrap up. So I'm going to try to make these cards. So I would like to capture how can limits be understood in the context of inputs and outputs. Let's see if that works. Perfect. I like that question. So the answer is limits describe how a function's output behaves as the input approaches a specific value. The input domain nears a point, and the output range trends toward a limit value, even if undefined there. This concept formalizes continuity, derivatives, and function behavior at critical points. Okay, so continuity here. We have discontinuity. Where was that discontinuity? Removable discontinuity. Okay. So continuity is about continual. Oh, okay. So what is continuity in? Okay. Okay. So continuity is when we don't have undefined points for a function, I believe. Nice. Okay. That's we'll see, but I think that's correct. Okay. See how this. Oh, I need to send that. Womp womp. Okay, so this little trick you can do with Anki. I guess it's not a trick, it's like a feature. Perfect. But you can like describe things, or rather, you can use HTML for formatting. And then it'll look correct. Okay, what is the mathematical syntax for limit in calculus? I think that's good. Oh, calculus question mark. I think I will have to go get that previous one. Okay. Okay, syntax for limits. We have, oh, we don't have. Okay, understanding them in terms of inputs and outputs. It's the input portion of a limit calculated. So I think the answer is here. Oops. Oh. Okay, this is what I was looking for. So if we go back to the input portion and the output portion of a limit, the input portion is describing what the limit is. So for limits and a given question, would I typically have the, like, as x approaches to limit for a function, or do I have to find that sometimes? And if I do, could you restate in less than 50 words how I might find that? And if you use mathematical syntax, please specify the entire answer in HTML. Oh, shoot. I need to remember to wait just a little bit for the Windows to process that fully. Okay. So I think we will. Yeah, I think we'll end here, and then shoot for tomorrow. Look, we made it 8 minutes in. We are insanely amazing. Okay. And then I feel like I'm learning. Okay, so this is surprising. I thought I wouldn't learn as much in this, and I have. So this is great. Yeah, I'm like super hyped. Like, one thing that's interesting is the conceptual. So I didn't really think about much about the process I would use going into learning calculus, and I was surprised by how much I'm focusing on the conceptual. I guess it makes sense. I didn't think about like, oh, would I do like more, mathematic, like, or would I focus more on the mathematics of it, or focus more on the concepts of it? But it makes sense because my background like is not too mathy. But I don't know. It's just really been really fun to interact with the concepts like this, and then also, I guess one point on me describing something as surprising. So when you are surprised, so I've talked about like having a hypothesis for something, and the fact that having a hypothesis can enable you to prove yourself wrong in a particular domain. Noticing when you're surprised by something is good, because then it describes a way in which your model of the world was incorrect. So even though I hadn't explicitly talked about it, I guess when I was going to go into calculus or like learn calculus, I didn't think that I would focus so much on the conceptual before even touching the mathematical portion, but it makes sense. And I was surprised by that. So being that I'm surprised by it, that means I need to change my world model such that, okay, it's probably the case that when I enter into a new mathematical field, or like want to understand a different branch of mathematics, that like maybe I'll go once I get like a greater, basis of mathematics, then maybe I'll just go from a more mathematic angle. But it seems like that I'm much more amenable to like a strictly conceptual for the first portion to really understand the ideas, and then wade into the math. So that is surprising, and I think it is good. Good at least to know, right? Actually, excellent to know. Let's see. I don't think there are much other things that I'm from that. But yeah, to recognize when you're surprised is actually an excellent thing. Okay. Yeah, I think we will end there today. So I'll just like say, start back up here. And then I'll also, lest we lose our spot in the video, oops, which is not likely, I'll also place that there. Okay, perfect. Sweet. I think that was a excellent day, and I'm excited to get through the rest of this video, because I think after we do that, like, things will be looking pretty good. And then we just kind of go hard on the mathematics for what it means to take something from a regular function, or I guess my, yeah, let's write this down. So I think the next things that I need to do, understand the syntax more. I need to be able to calculate a limit. Be able to take a derivative. Be able to take an integral. Be able to evaluate a definite integral. Okay, I did take a little peek at this calculus book as well, and so I'm cheating a little bit, but and I think reasonably so. There's a lot more mathy parts here. We got a lot more like equations and expressions. And we also do have some proofs. And I have exactly 0 experience with proofs. So probably something more in that regard as well. Yeah, so maybe proofs question mark. But I'm not sure if proofs is like, maybe you get a little taste of proofs in calculus 1. I'm not sure if this is just calculus 1. Who knows? But yeah, I think we are at a good spot. So I will end there.